Okay. Yep, now we're recording. You are unmuted and you are, let me just change this side-by-side speaker. And I close the chat. Do slightly bigger. There we go. We're ready.
All right. Hi, everyone. It's a pleasure to be talking not here, but there. From your point of view, it's a pity to not be there. Still, I'm really excited to talk about this work. This is joined with David, who is there, so you can pester him later about this. What I'm going to talk about is cybernetic systems, which is a classic from myself. What are these? These are parametrized systems. So basically processes, which I call plans, that come with an extra baggage of a controller that is a system that does something and fits into the process. And of course, these can be bidirectional. So it's actually a action-reaction process. So 2 years ago, me and a bunch of other Strathclyders presented a paper where we outlined some ideas on how to go on about specifying the cybernetic systems using the language of actegories and the language of optics. Here, I'm not going to talk about optics, but the rough idea was that you can have the controllers coming from some symmetric monoidal category of control processes, and then they act on a symmetric monoidal category of processes. And then on top of that, you have this category here indexing sets of controllers that give you like these little bubbles here. There's a way to justify these diagrams before someone asks me, but we're not going to see a lot of them. So examples of this are basically you have the symmetric monoidal category of lenses, and as controllers, you have selection functions, which are some ways to specify players' incentives in game theory. Or you can have smooth functions as your processes, and then you have generalized Riemannian metrics or symplectic structures on them as controllers. Okay, so you see these are things that are not really like processes, right? Are systems, so they stay there and they tell the plant, the process, how to behave. Now the problem with this, oh no, not yet. So once we have this, we do the power construction, which is the star of this talk, and this power construction packages all this data into a single symmetric monoidal bicategory, okay, where the first dimension gives you like processes and how processes compose, and the second dimension gives you a composition of control plans, of control processes. So these things here are just plans coupled to a controller, as I said in the beginning. And if we do this for the examples we were talking about before, we get, unsurprisingly, open games and open gradient-based learners. Now, what's left out from this picture is behavior. Okay, so we're interested not just in specifying the systems we have, but also in specifying what they do compositionally. Okay, so once I have this nice compositional description of a game, for example, I might be interested in computing the equilibria, or if I have some model of some differential system, I'm interested in computing its solutions, and so on and so on. So David, a couple of years ago, introduced a very, very nice framework to do systems theory from the behavioral standpoint. And I'm going to butcher his entire work here and say that the idea basically is to have processes not just organized in symmetric monoidal categories, but in symmetric monoidal double categories, where the extra dimension gives you comparison maps between processes, okay? And it turns out that behavior is often functorial in this direction, and moreover is often co-representable. So it's given by mapping a specific system into another system, okay? For example, the system that does nothing gets mapped into every other system, and these maps give you equilibria of these other systems, because these are the behaviors of the other system that are like the system that does nothing, so they stay still. So can we do this for cybernetic systems? And the idea would be to promote each of these ingredients to like a double categorical version thereof. For example, you would have, instead of a symmetric monoidal category of control processes, you have a symmetric monoidal double category. And then instead of a monoidal copreship, you have a double index category, which is what is called a theory of systems in the categorical system theory framework. What's not really clear is what to do with the action, because an actegory is a pseudo action in cat, whereas here we're in a completely different setting. It's also not clear what to do with the para construction, because like para construction is very hands-on. So how do we generalize it to this very different setting? So this is what I'm going to talk today about. So first of all, how to generalize this para to work into a generalized para to work in two categories which are not cat. And we're going to see that this leads naturally to this notion of hybrid action, which is very interesting and is also secretly needed in categorical cybernetics. And then I'm going to show you some examples. So how to, like, I'm going to instantiate this construction for the setting that we actually want to use it for, which are process theories, so symmetric monoidal double categories. And then I'm going to show you some example of what kind of behaviors we can represent if we're using this technology. And then if there's time, I'm going to show you why there's an org, which hopefully David talked about to someone lately. Why these two things are actually very similar. And there's a good news because, yay, we're all having the same ideas. That's great. So let's start with the description of a generalized para. So para is a functorial construction that takes an actegory, which is a pseudo action in categories, and gives you a bicategory. It's actually a bit better to have this land in double categories instead. This is going to help the generalization. So given an actegory, para is going to give us a double category whose loose arrows are parametric morphisms and whose tight arrows are morphisms in C, so the category being acted upon, which have no parameters. And then a square is just a map between the parameters of the sides that makes the obvious square commutes, okay? So basically here we added these external parametric maps that are not there in the bicategorical version of para. Okay, so once we have this, it's really easy to replace cat with K in our notation and be like, okay, we're done. Here's a para construction for any K that's nice enough to have this work. But how do we actually do this? How do we actually define the functor? So here we have to be a bit clever and see how we can define para without actually like going there and define stuff, but doing functorial operations. For the first thing to notice is that para, at least parametric morphisms, can be built with as a comma construction. Okay, so the obvious commuting square I was talking about before is this square, and this square is a morphism in the slice of the action over C. So that's a very abstract way to define at least a piece of the data for para. In any category, it has comma objects. And the pseudo category structure is a bit more tricky, but very, very interesting. So first of all, remember that any comma square can be defined as a pullback, a strict pullback in my case. And you see here, instead of the identity, we have now this domain projection out of the power of C by the walking arrow in cat, okay? And once we have this, then it's really natural to add two little wings and see this as a composition of spans, okay? And these spans are very interesting. So the first span is basically given by the actegory structure of, well, the pseudo action structure we're talking about now, okay? So this is the action map and this is just a projection, but then if you ask this to be a pseudomonad in span, then, which is a weak notion of monad basically, then what you get is all the data that you would specify to specify the monoidal structure on U and the actegorical structure here. So asking for this to be a pseudomonad appears to be like a direct generalization of actegory. And on this side, we have another very natural pseudomonad, which is that of squares of C. So this is like a generalization of the doubles category of squares for a C living in a two category with powers by arrows. And then when we do the composite, what do we get? We don't just get the parametric maps as objects here, we get the full graph structure of the double category or the internal category in K we're looking for because these two legs project to the domain and codomain of a parametric map, which is an object here. So now we have just to find a pseudomonad structure on this big span, because remember the pseudomonads in spans are pseudo-categories, okay, which is just a weakened version of the classical fact that monads in spans are categories in whatever category we're working in. And how do we define the pseudomonad structure? Well, we can define it directly because we know how parametric morphisms compose, okay? They have this finite composition law where you have the parameter of the second map, this should be of course a G. The parameter of the second map gets to act on the first morphism altogether, and then with Q's fixed, we do the first morphisms, and then we do the second. And it turns out that you can reproduce this abstractly by specifying a pseudo-distributive law between the two pseudomonads we composed. And the pseudo-distributive law only uses the fact that pi c, so this projection morphism, is a fibration. So why not using a fibration there instead of a product projection? And if you replace this piece of data with an arbitrary fibration in K, and you still ask for this thing to be a pseudomonad, then you still get something that works. So when you compose this with this, you get a new pseudomonad because you have a pseudo-distributive law of this over this. And it's basically given by pulling back the parameter that you have on B over A using the fibration structure, and then having the parameter act on the whole thing as before. And this brings us to the first definition of the talk, which is that of a fibered action. And a fibered action is substantially a pseudomonad in span whose left leg is a fibration. That's it. And this is the kind of action that this para construction consumes, okay? So I'm just gonna give you a little bit of intuition of what this is. So I'm going very fast, so I don't expect you to like understand all the gory details, but just this intuition. So the intuition around the fibered action is that whereas in a regular action, we have an object acting on another object, and these two things are independent. So once you choose something in C, then whatever is in the other category acting on C is going to act on it, and you can choose anything. Instead, in a fibered action, once you choose a thing to act on, then you get an object of scalars which is dependent on that. So you vary your scalars as you move around your category. And the chief example of this is this little guy which we've seen before, in which the things that act here are morphisms. So what's in here, if you think of this as a category, are morphisms in C, and the way they act is they send their domain to their codomain. But so you see the dependency of the action, P, which goes from A to B, can only act on A, and in general, A can only receive actions from morphisms going out of A, okay? But another reason why we might like this notion of action is that, okay, we might have something that looks like an action of the regular kind, but has different morphisms between the parameters. So morphisms that now depend on the thing they're acting on. So for example, we have a Cartesian pseudomoid in K, so think of a Cartesian category, then this can act on itself because it's a monoidal category, so it acts on itself by Cartesian product. But we can also form this simple fibered action. So this thing on the left is like the simple fibration. And the objects here, so think of this as categories again, are simply pairs. So as if this was C times C, but morphisms are not pairs of morphisms that are unrelated. So it's not A to C and B to D. It's A to C, but then you have A times B to D, okay? So you have this twist, this difference that you wouldn't be able to get if this was just C times C. And so if we're just looking at actegories or pseudo actions, if you're generalized, okay? So this is gonna come handy later. And you might ask now, well, this is never going to be useful, Matteo. You're just generalizing because the category theory is nice. And that's what I thought. And then it turned out that actually these kind of actions, because of the phenomena I just showed you, are crucial to get right what we actually want to get right. So this is one of the amazing miracles of math where generality just allows you to be in the right place at the right time. So let's recap what we did. Basically, we moved from cat to an arbitrary two category, which is suitably complete. And then we observed that for a certain kind of actions that we call fibered actions, which are given by pseudomonads in spans where the left leg is a fibration, these are the right ingredients to get a para construction out of. And it's this thing here. And David gave a talk at last CT about this and why this picture is actually not right. And there's a lot of little details I left off, but this is what we need today to go on to applications. So if you want to pester him, I invite you again to do so. So let's see, first of all, I want to talk about parametric open dynamical systems. So let's see first open dynamical systems. So Myers defined this nice double category called arena, so there's one for every fibration, right? And given a fibration, you get a double category where the objects are basically objects of B, so bundles. Think of this as bundles. And then you have two kinds of maps. The horizontal maps are charts. So these are like algebraic maps of bundles, mapping a thing on the bottom to a thing on the bottom, a thing on the top to a thing on the top. And lenses are like charts, but the second map is flipped. So it goes in one direction on the bottom and in the other direction on top. And so we think of this as bidirectional processes. And then this double category describes how you can map these double bidirectional processes to each other. And a square here is simply a commuting map of processes. So this splits as two squares whose commutativity basically says that if you do this process and then you map it to this, you get the same thing as if you do the other thing. Okay. So examples of this are if you have Q being the codomain fibration for sets, you get something that looks like poly but has an extra dimension. And instead, if you choose something more structured, more geometrical in flavor, like the fibration of submersions of manifolds, then you get differential bidirectional processes and maps thereof, okay? And also here, I note that if Q is a symmetric monoidal or a Cartesian monoidal fibration, then this double category inherits the same structure. So let's assume this. Let's assume Q is Cartesian monoidal. So we can do this construction I showed you before of the simple fibered action, okay? So remember, this is basically arena times arena acting on itself by Cartesian product, except that now we have this extra maps in it. So I'm gonna claim three things. First of all is that the ambient 2 category I'm working in is the kind of ambient 2 category I can work in for my goals, which is a 2 cosmos. And there's a very handy paper that came out very recently that allows me to say this. Secondly, that this is a fibration of symmetric monoidal double categories. And again, there's a paper that came out recently that helped me saying this. And finally, that this is a pseudomonad, and this is quite easy to verify. Because again, think of this as arena acting on itself by product, okay? So all in all, we have a fibered action, and this means we can apply the para construction to it. So now I'm gonna tell you what this yields. So we've seen that applying the para construction to a fibered action yields a pseudo-category object in whatever ambient category we're working in. And a pseudo-category object in symmetric monoidal double categories is a symmetric monoidal triple category. And I want you to notice that this structure, this monoidal structure is now comes for free by the abstract nonsense behind the para definition. So it's not something we have to prove on top. And this also works in like the classical cases in categories. But anyway, let's see how this triple category is looks like. So first, the zero cells are the same as in arena. So these are bundles from whatever fibration we chose. So think polynomials or submersions of manifolds. The one cells are 3 kinds. There's the kind we already seen, so lenses and charts, but there's also a new kind, which is parametric lenses. So you see, I didn't bother writing all the objects because it gets messy very quickly. There's also three kinds of two cells. So one kind is, again, the one we already met. This is a square in arena, so a commutative squares of lenses and charts. But now we have also commutative squares of lenses and parametric lenses and lenses, which represents a process happening in the parameter direction. Okay, so this is something that is built on top of this parametric process and extends this process in the parameter direction. And then there's a third kind of two cell, which is now a comparison between parametric lenses. Okay, so now we have charts. So this is a square that is like the one we've seen in arena, but now there's also an extra data inside the square that is a chart between the parameters. So it gives me a way not just to compare the boundaries of a process and asking everything to commute, but I also have this extra data to compare the third boundary, so the parameter of these two parametric lenses. And finally, a cube, so a three cell, is what happens when we put everything together, and you see this basically amounts to a square in arena. How much time do I have left?
Minutes plus 5 minutes for questions.
Okay, so I'm gonna just quickly show you what we read from this. So first of all, if you have a game, an open game, then I wrote a paper last year where I showed that this can be like compiled down to something that's one of these basic two cells in Power Arena. So it's a lens here with a parameter here, and this is constructed in a certain way. And the way it's constructed is such that if I now map the trivial parametric lens, which lives now in the back here, if I now look at a map here, so a cube from this to this, this singles out exactly the Nash equilibria of this game. Okay, in other words, so all this data here collapses to a square like this in arena. So you see here we get a state, we pick out a state, we pick out a strategy profile, and we pick a payoff function. And then the commutativity conditions on this impose that the strategy profile is a fixed point of the best response function. So it's a Nash equilibrium. So now we have a way to represent Nash equilibria of games as behaviors in our theory, and not just as things we bolt on top, which is really nice and really intriguing. And finally, we can do the same for control ODEs. So if you have a control ODE, which is an ODE which has an extra parameter space intervening, and is also open, so it has an input and an output thing intervening in the dynamics, then if you want to solve this control ODE, you can represent this solution as a map from a system called the clock. So think of this as the walking trajectory. It's just a differential system that flows in time without doing anything and changing at a constant rate. So like a trajectory. So if we map the system to our control ODE, what we get now is something that corresponds to a square like this. And now you see that it's crucial here that we're using the simple fibered action of the trivial action, because if this wasn't the case, then here I would be picking two separate trajectories, one on the states and one on the controls, using two time coordinates, which is not what we want. We want them to share the same time coordinate, and using the morphisms you have in the simple fibration is exactly what you need to fix this problem. So now once you have this and you have solved this problem, then you get from the commutativity condition exactly the condition that these maps are picking out trajectories that solve the open control ODE. And I'm gonna skip this bonus content. So in conclusion, I told you what is this thing I wanna do, which is to do behavioral categorical cybernetics. And then we can do this by generalizing the power construction and inventing this new kind of action, because it's always a good idea to do. And then these new kind of actions turn out to be really useful to solve the problems we have in categorical cybernetics. What I didn't tell you about is, again, all the nitty-gritty details of this generalized spiral construction that is quite tricky to get right. And the bigger picture, which is how to actually do this for not just double categories of processes, but double index categories of systems, so that we can actually get this right. I sweep some details under the rug in the last two examples, but we just don't have time. So thank you very much for your attention, and apologies if I ran a bit over time.
Thanks, Matteo. David's hand shot up immediately.
How does this compare to the org thing?
Thank you, David. I really saw this coming. I'm going to give you the short version of these 3 slides. So David certainly knows what org is, since he defined it together with Brandon. For the people who don't, it's a double category where you have basically parametric lenses on the loose direction, normal lenses, non-parametric lenses in the tight direction. So this looks a lot like Pararina already, right? You have parametric lenses and non-parametric lenses all together. And then here you have this F, which is a morphism of parametric polynomial functor, parametric lenses. So it's something that maps parameters to parameters and commutes with the dynamics, basically. The difference is now that this F is not like, is unlike the ones I had in Pararina, okay? It's a bit different. So you can map a square in org to something a bit awkward in Pararina. Why? Because this square here is sort of mixing different aspects of parametric lenses, you could say. So on the one hand, this square is made of dynamical things. So this alpha and beta are not encoding a map of interfaces, okay, but are actually dynamical things. And on the other hand, this square is doing a mapping which is static. So it's witnessing the fact that this composite dynamics can be mapped into this composite dynamics. So when we map this in Pararina, we separate it all out and we divide it in 2 kinds of square. This F, so it maps to a chart, something that lives in the horizontal part. You can, of course, like assemble this back into just a square. But I mean, this is not exactly the same thing. Pararina is a bit bigger, contains more stuff. But it's interesting that we converge on the same structure, so I'm really happy about this. And that's it.
Great, thanks, Matteo. Any other questions? Well then, thanks again, and it's time for lunch.